Okay, so hello everybody. My name is בת-Xen. I'm a PhD student of Orna Greenberg, which you all know. And today I will be very briefly talking to you about our joint work from FM 2016 about sound and complete mutation-based program repair. So what is mutation-based program repair? In this work, we are focused on sequential programs, which contain the usual constructs, assignments, conditionals, loops, and function calls. We also assume the code comes with built-in assertions written by the programmer. And we know that at least one assertion violation has been observed, and this is the bug. And what we'll try to do is to automatically repair the program with respect to this bug. How do we do this? We have a predefined set of what we call mutations, which are syntactic operations that we allow in order to make changes to the program. These contain, for example, operator replacement, replace a plus with a minus, or constant manipulation. If you have some constant in your program, you may replace it with its value plus 1. And these are very simple syntactic local changes to the program. And we have a predefined list of what we allow. And the question we ask is, can we use this list in order to make all assertions in the program hold? And sometimes there is more than one option. And our goal in this work was to return all possible options, all possible repairs. So here's a quick example. This is a function f that gets two inputs. Do not try to understand what it does because it's nothing significant at all. But for the input, x equals 5 and y equals 2, here's what we get. This program checks if their sum is greater than 8. It is not, so z gets the value 9. And then we check if z is greater or equal than 9. It is. And z gets the value 8. And now the user says that it expects z to always be strictly greater than 8, and it is not. Thus, this is a bug. And let's say we want to fix this bug using this very simple mutation list. You can only replace a plus with a minus and the other way around, or replace the greater than operator with a greater equal, and the other way around. And you're allowed to make any number of such changes from this list anywhere in the program. So can we fix the bug I just showed you with this list? Usually I'll let you think about it a little bit, but now I will just tell you the answer. Are we allowing questions? Because I only have 6 minutes. I'll answer in the end. So what we can see here is that at this point in the program, it is guaranteed that z will always be greater or equal to 9, because we either assign 9 to it or we assign the sum of x and y after we check that the sum is strictly greater than 8. So what happens here is that if z is greater or equal to 9, then we decrease z by 1, and we expect z to be strictly greater than 8. So this line here is problematic, and there are two ways we can solve the problem. One way is we can replace the greater or equal with a strictly greater than, and now we won't have this problem anymore. And there is also another way to fix this problem, which is to replace the minus with a plus, and then, of course, z will always be strictly greater than 8. So what we would expect our algorithm to output in this case is a list with two options, one that says replace the greater than with the greater equal with the greater than, and one that says replace the minus with a plus. How do we do this? Very, very shortly, I'll explain an overview. We make a reduction from our original program, which is to find all correct programs from a finite set of optional programs created using our finite mutation list. We reduce this problem to the problem of finding all unsatisfiable constraint sets from a finite set of constraint sets. How do we do this? In 3 steps. First, we have the translation step, which essentially translates the program line by line to a constraint. So if we had, for example, at line 3, we had this simple assignment. After translation, we'll have a set of constraints for each line, and for this line we'll have something that looks something like that. Of course, I'm not explaining all the details here because I don't have time, but the second step will be to apply mutations, and what we'll do, we'll take this simple constraint here, and we'll replace it with a set of constraints, which is all the options for this specific line. In our case, there are only two options, one with a plus and one with a minus. And now to find the repair, for each line we have this set of all options, and all we have to do is to choose exactly one constraint from each set. This will constitute a program, and that program will have to check if the conjunction of the constraint is unsatisfiable, then we'll know that this program is correct. And to cover this search space of programs, we'll use some kind of interplay between a SAT solver and an SMT solver. This all has been very confusing, and of course, this is not enough details. So please come check out my poster today if you didn't already check it out yesterday. This is your last chance, so please come and I'll take questions happily. Alla bada. Thank you.
Thank you. I see a question here.
So I'm wondering, what do you mean by correct program here? Since if you don't, for example, in your example, if you don't specify what this program should do, then if the operational definition of correct is only that no assertion is triggered, then I have plenty of ways to fix the program. And after those fixes, each program might have different behavior. So what is your definition of correct?
Our definition of correct is only with respect to assertion. If you had an assertion that says x is greater or equal to 0, and somehow you manage to always make x 0, then this program, I consider it correct, even though you are very, very much onto the problem that it may not be what the user wants at all. But this is a general problem in program repair, not just by using assertions. Most works in this field use a test suite. So they say, well, if all the tests passed, then your program is correct, which also has some kind of problem with overfitting. So we used assertions instead of test suite, but we still have the problem that assertions alone are not a complete specification. Yes?
Okay, sorry. Have you at some point considered that the assertions might be wrong? So do you also take into account that you might want to change your assertion?
We didn't, but to add that, it would be really straightforward in our approach.
You have a question too? Different question?
Oh, hey.
So in your example, the assertion was in the end. Assertions may also be in the beginning to denote some preconditions, and they fail when a client of this method, whatever it is, calls the method with inappropriate inputs. And so, can your methodology fix the clients if they crash if I put, for example, in a square root function in the beginning,
You have.
x.
Let me just stop you right there, and if it doesn't enough, then you'll continue. We have also assume statements, not only assertions. So for what you're saying, it would be more appropriate to put an assume. We assume the input is something, and we do not try to repair the program with respect to assume statements, only with respect to assert statements.
Assume is something else. It's a static verification statement that
Yeah.
it corresponds to a runtime regular assert statement. Yes, you use assume for static verification, but at runtime they are still assert statements. And so can you fix if a client calls some method with bad inputs, and inside of the method an assertion crashes, so can your methodology fix this inappropriate call in the client of this object or method?
In this work, we can only fix crashing assertions. So if the function calling my function is also within the scope of my repair, and in there you added some assertion that says don't call this function with this and this input, then I can. What you're suggesting is the user call the function with a bad input, with an in. Oh, sorry, that's how I understood your question. But yeah, we'll take it offline. Okay. Thank you.
Hello. So I'm Carolina. I'll talk about runtime verification for fixed-point logic, or how to synthesize optimal monitors. So runtime verification, it's a little bit like model checking for lazy people. You, instead of looking at your state space of your system, which, you get state explosion and all of that stuff, you just have it as a black box and you just look at what comes out. So you look at executions and then you attempt to infer some properties of your system by only looking at what it produces. So, of course, that's going to be very much weaker than model checking, but it's a lightweight alternative or a technique you can use in addition to model checking. Model check part of your system or part of your specification, and then combine that with something cheaper. So in the setup, we have a process, your system, and I'm interested in specifications that are expressed in Hennessy-Milner logic with recursion, which is essentially modal mu calculus without propositional variables. And here what's important to note is that our specification language is over properties of systems rather than properties of traces. So we can't expect to get model checking of these specifications by only looking at traces. So we're interested in, well, what can we do? So imagine we have a monitor, so either a rejection or an acceptance monitor, which observes traces and can reach either an indecisive state, or it can reach a state that says, right, this is definitely wrong, which will refute my specification. And that is defined by an instrumentation, which can lead to one of these two outcomes. Now, the question I'm interested in is, well, what's a good monitor? If I have a formula and I want to do some runtime verification, what monitor should I use? And, well, what does it mean for a monitor to be good? So we can define some nice properties of monitors, such as it being sound. So if my monitor rejects a process, then that should guarantee that that process does not satisfy my specification. That's a sort of basic thing you want. Then you can also talk about completeness. So maybe you'd like your monitor to be able to reject all processes that do not satisfy your specification. However, that's quite a lot to ask. In fact, if you ask both of those things, it's been shown that you can only get such perfect monitors for a very small fragment of our logic, namely the safety fragment. So what I'm asking, well, what if your specification is not in this fragment? Then, well, what do you do? There's two things you can do. You can say, well, okay, I'm not going to do runtime verification. I'll go to the pub. My approach is slightly different. I would say, well, let's see what's the best we can do. What can we define some idea of when is a monitor good and better? So there's a fairly natural thing to do is to say, well, I want the monitor that rejects everything that any sound monitor can reject. And we can ask, well, how do we find that monitor? Now, so it turns out that this problem of finding the optimal monitor reduces to a fairly sort of easy to describe logical problem. So we have our whole logic. We know that some fragment of it has perfect monitors. Now I have a formula outside of this fragment, and I'd like to find the best monitor for it. So it has a bunch of consequences in this safety fragment. might have an infinite number of consequences in the safety fragment. And we're going to look for the best one. And what I mean by the best one is the strongest safety consequence of our input formula. So we have this formula here that will also imply all of the other safety consequences of our input formula. And we can show that this strongest safety consequence, it also has of this perfect monitor, and the perfect monitor for this formula will be the optimal monitor for our input formula. So then all we have to do is to, well, generate this strongest safety consequence, which we can do using modal mu methods, some formula manipulations, which will get us from here to here. If you want to know more about those methods, I have a poster today and tomorrow. You can also come and talk to me about parity games if you want, in particular about how the recent quasi-polynomial solvability of parity game, what does that have to do with the modal mu alternation hierarchy, if you want. But I don't have a poster about that. Thank you very much. Yes?
What do you monitor?
What do I monitor?
Usually when we talk about monitoring, there's some software running,
Mm-hmm.
and you monitor the state of the program. What do you monitor?
So here, this instrumentation relationship, it monitors, so we have a process that takes action. So it monitors the sequence of actions.
Processes don't take action.
So the,
Processes are mathematical models.
yes. Okay, so if we write our process as a CCS process, our monitor will, so it will execute in tandem. So if the process executes an action alpha, then either our monitor can also execute that action, or it can say, oh, I can't monitor this.
So it monitors the actions
Yeah.
of the process?
Yeah.
I see.
Can
Mhm.
this kind of monitor somehow predict the future? By prediction, I mean that can it observe the action of this process up to now and predict that it is going to fail after several execution? Because if it only can tell that it's failed at this moment, then it's not very useful, right? Since I can already tell that the program has failed. I don't need this monitor. So, I mean, if it can somehow predict the future, then it will be more useful in practice.
I agree. Predicting the future sounds like a very useful thing to do.
So is it possible that your monitor can do this stuff?
I don't see how.
No, you're probably meaning the sense that Javier was talking about, just predicting what the future has to do in order to satisfy the specifications. And this is what the monitor is doing.
Sorry.
Okay, more questions? Thank you.
But I don't. Oh, yes. Thank you.
This is a good time to remind all the speakers of today, tomorrow and the day after to come before the session. Tell me that they are here and move their talks to the single lecture. You have 5 minutes.
Okay. Last week I was attending to a lecture about the art of presenting science, and it gave me an idea to present intuitively my work. So when you want to make a presentation, you first think about your talk and try to modelize the structure of your talk. So you have some expectation and you develop a formalization of it and then verify that it matches your expectations. But then when comes the day that you face the audience, well, you try to go through this modelization, but you're in front of an audience that you don't know. and you have to compose with it. So this is the illustration of an autonomous system interacting with unpredictable environments. So now the question is, can I still reach the expectation that I was writing yesterday? Well, first try to formalize this autonomous system. Then I will use this formal model of constraints automata. And well, my autonomous system has some action. He can read what is written here, or he can try to improvise. And he will do it as follows. He has two states. He first starts in this stage and can either read or improvise, and will take the transition that has the least cost. So as long as he can read, he will read. But when he can no more read, he will improvise, and improvise as long as he can improvise. So it models what the actions are possible for my system. But it also has a mood state, and it can be excited, it can be bored, or it can be calm, and alternates among those mood states following the equivalent automata. So now, if I think about the teacher system, well, I can compose those two automata. And what I get is all the possible states my teacher takes by composing the different actions he does with the corresponding preferences. And from this model, I can apply verification before the real-time simulation to see if this model corresponds to my expectation. If it does not, then I refine my model as long as it matches my expectations. But then, when it comes to the real-world situation, my autonomous system is in interaction with unpredictable environments. And while we can think about a simple model of these environments, which has, I'm sorry for this simple system, but has two transitions, can either sleep or listen. And because it's the end of the day, he prefers to sleep and listen. And what's the consequences of the environment is that it will impact my transition system in a certain way that I cannot predict. And the observable behavior is modified. Then the next day, I can look back at my talk and observe some trace out of the talk, and I can look at all the states I jump in during this presentation and see that I reach a certain kind of behavior that I don't want. Is an infinite loop on the boards and reading states. So what I want is remove this possible trace of my behavior. And the strategies to remove this trace is either to look at my initial components and modify the preferences in order to remove the trace out of my possible behavior. But I can also interpret this trace as a property that my system respects. And by negating this property, I would like to be able to represent this property as a new component on my system that I can compose with. Thank you. Yes.
What happens when you block this trace? Doesn't the system just deadlock?
When you block the trace?
Block this trace, but the environment behaves in this
Oh, yes.
undesired way.
So,
And you're
yeah.
blocking it, simply means you're just in a deadlock now. No?
Yeah, that's indeed. So if the behavior you want to remove is intersecting with your expected behavior, it can lead to a conflicting situation, and so it has this. The removing of the trace has to be coherent with your initial expectation. So by deadlock, well, you can reach a deadlock, and then yes.
Well, if the input, the environment feeds me A, and I say I don't want to read A, what happens now? Somebody
Probably
comes and push-
what's
somebody comes
happening.
and pushes the T
Yes.
button, and the vending machine says no, I don't want to give you T. What happens now?
Yes. Good question. Um, yeah, that's a good question. I don't know.
Time until the poster to come up with the answer.
Yes, I'm almost in this deadlock state now. I can.
That's a good answer.
Okay, yeah, hello. My name is Marcel and I'm from the University of Aachen, which is in Germany, located near Cologne, which you might have heard of. And my subject is the automatic inference of the expected runtime of probabilistic programs. So I'm going to explain to you what that actually means. So far, we have considered the automatic inference of the runtime of deterministic programs. And here's an example of such a program. We have two program variables, x and n, and here this is an assignment. X is assigned the value of n, and we assume that they take integer values. And then we have a while loop, which is very simple, where x is just decreased by 1. And now the question is, what is the runtime of this program? And here the crucial point is the estimation of the number of loop iterations. And how do you do that usually? You construct a ranking function. And in this case, a ranking function would be this one. We have two program variables. So we map from z2 to z to the first program variable. And this is a ranking function for the loop. And why is that? Whenever the loop guard holds, r is strictly positive. And in every execution of the loop, x is decreased by 1. And if you have a look at the ranking function, this means the value the ranking function takes is strictly decreasing. And therefore, we can argue that the loop is executed at most max x 0 times. And then by static analysis, we can find out that x has the size of n. And therefore, we can say that max n0 is an upper bound on the number of loop iterations here. And in this special case, it's also the exact number of loop iterations. And this has already been automated and published last year. Now, the question is, what happens if we allow assignments to be probabilistic? This was a deterministic assignment, x is decreased by 1. And now we assign x by a kind of a coin toss. And whenever we toss heads, x stays as it is. And whenever we toss tails, x is decreased by 1. And now again, the question is, what is the number of loop iterations? And as you can see, for a fixed input, you have many different program runs due to this coin toss. And therefore, the runtime is a positive random variable t. And the probability in this case that we have m loop iterations, where m is some number greater or equal to n, is this term, which is already very involved for such a very simple program. And this is due to the fact that when we have m steps, we know we have n times the decreasing by 1. But the last step, we decrease by 1 and then we reach 0. So we only have n minus 1 left. And so we can choose n minus 1 out of m minus 1 to be the decreasing ones. The other ones are the ones where it stays as it is. And as we toss the coin m times, this is the probability. And now we can see, or we can compute that the probability that the runtime is finite in this case is 1. And this means we have the so-called almost sure termination, which is exactly the probability of all terminating runs is 1. And even more, the expected runtime which is the expected value of this random variable, and this is the definition of it, is 2n, which is smaller than infinity, and therefore we have positive almost sure termination, meaning we have almost sure termination, but the expected runtime is finite. But now the problem is, as usual with termination, AST is undecidable, and PAST is even higher in the arithmetical hierarchy, and therefore it's very difficult. And the question is how to do this fully automatic and infer bounds on this expected runtime. And just to give you an example what difficulties can arise, if we add a second program variable, which is increased by the value of x in here, which is kind of a Gaussian sum, and then we add a second loop where this program variable is just decreased until it's 0, the expectation of y after this first loop is quadratic, but these loops both have just linear expected runtime, but in the end it turns out that the program has quadratic expected runtime, which is something that can happen and which is so far not known how to deal with. So to sum up, the objective is the fully automatic inference of bounds on the expected runtime, and for pattern matching this is my poster. Thank you.
Any questions? Yeah?
Yeah, I don't know much about this. Can you give us a little bit of insight of how you do that for non-probabilistic programs, like automating the like finding the expected runtime?
Okay.
How do you automate finding the ranking function?
Okay. If you want to find a ranking function, you usually just ask for linear ranking functions, and then you kind of generate a template for a linear polynomial, and you have conditions due to these two things that you want that the ranking function satisfies, and then you give this to an SMT solver, and then he gives you the ranking function. Yeah.
I'm not very familiar with this topic, so please correct me if I'm wrong. Since you say that this problem is undecidable, but it occurs to me that it is very similar to a random walk on a graph. So if we translate each state of this program, the state variable of this, the variables in this program as a state, then it's kind of like you are doing a random walk on this graph, and some of these states are accepted. And the question becomes that what is the expected time that this random walk takes to visit all, maybe one of these accepted states? Then I think this problem is well developed. There are algorithms to compute this value. So I'm not sure why you say that it's undecidable.
Sorry. So your question is
For
why?
example, in this example, it's just a one-dimensional random walk, right?
Yeah.
So you can compute like this. So I think for general graph, there is also some arithmetic result that you can compute this expected time. So I'm not sure why you say it's undecidable.
It has been proven to be undecidable.
Maybe.
A random walk is like doing +1 and -1, and that's it. And here you can do much richer things.
But if you can still model it as a graph, right? Each variable. So there are.
Yeah, the actual thing which is underlying is a Markov decision process. Yeah. And yes, and then you have, like with Markov chains, you have null recurrency, positive recurrency, and transiency. And these are the things like null recurrency is AST, and positive recurrency is PAST, but they are both undecidable for these. And it turns out that the universal PAST is even undecidable if you have an oracle for the universal halting problem.
So it's not like expected circulation time in a random walk. So you are not searching for this answer.
I think we should maybe discuss this later at the poster. Oh.
I'm having a hard time reconciling the last two lines. It's more decidable, but I have a fully automatic tool.
Of course, whenever you try to find a fully automatic tool, this will fail in some cases. But we would like to have a tool which can at least deal with popular cases or with most of the cases here. But of course, you're right. If it's undecidable, then you won't find a fully automatic tool.
So I'm not planning to present something during the school though, so this is completely on the fly. But so it should be a good exercise to present my work on my PhD student. PhD. So I'm excited to introduce.
Clean up the rest of the book.
Okay.
I'll keep for it.
Should already write the name. So, I'm really excited to introduce you weighted chop automata as a formalism, a decidable formalism for quantitative languages. So in verification, we use at many times languages as a tool for speak about the behavior of a system which can be seen as a function from a finite word to a Boolean value. But sometimes it can be useful to not just speak about correctness of the behavior of the system, but also the performance, like energy, for example. So we a little bit generalize the definition of Boolean languages to quantitative languages and take integer at the output. And all classical classical Boolean decision problem can be expressed in this quantitative formalism. I mean the emptiness, the universality, and the language inclusion. So the language inclusion should be FU for F and G, a finite representation of a quantitative languages. And so, in the literature, the most studied formalism for quantitative languages is max plus weighted automaton. So max plus weighted automaton is an automaton which carry some weights on transition. Let's take 1 and B return 2. So this is a pass, and the value of the pass is just the sum of all weights. And since in general automaton are not deterministic, we can have also another pass with another value. But to obtain a function, we just take the maximal value of the two accepting states. That's why we speak about max plus weighted automaton. But in 1994, Cobb proved that the language inclusion for the max plus weighted automaton is undecidable. And in 2011, Thomas Colcombe showed in a DAX tool presentation that the indecidability is already true, even if the max plus automaton is linearly ambiguous, which means that the number of accepting states is linear in the input world. And so, two important features for decidable formalism, and for these formalisms is first the unambiguity. Since already for linear ambiguous we are undecidable, so we need to be unambiguous, so we cannot have this kind of comportment, and so we just ignore the max since we are completely ambiguous. The second important feature is the closure property. In the literature, quantitative formalisms which enjoy nice closure property is mean payoff expression. This is a work of Thomas Enzinger and some other computer scientists. So a mean payoff expression is expressed by this grammar. Take a determinist mean payoff automaton, but let's just consider this is a sum automaton. We cast it to a finite world. And we can take the max of the value of automaton, or the mean, or the plus, or the minus. So this formalism is closed under those operation, but first we cannot express an ambiguous automaton is these formalisms. And the more important remark is the operation is just applied on the whole world. We cannot iterate something, a fragment on the world. We cannot apply operation just on a fragment of the world. So that's why we introduce a new model, the weighted chop automaton, which is recursively defined. So 0 weighted chop automaton is just an ambiguous unambiguous automaton, and n weighted chop automaton is, so as input we take not just a letter but a language, and since this here we have a notion of unambiguity, let's generalize the notion of unambiguity to language, and as input, as output, we do not just take a constant, but a Presburger definable function of almost finished of some sub weighted chop automata. So this is n-1 chop automaton, and so this model is undecidable for quantitative problem, but if the sub-weighted chop automaton decompose the input word in the same way, then we recover the decidability, and that's your principal result. Thanks for your attention, and sorry for...
Any questions? I have a question. So this is if you work with Z, and if you work only with positive integers, of course it stays decidable, but do you need other restrictions?
No, we work with not just positive integer. We can take also negative integer.
And what happens when you work with rational?
I'm not sure, but it can change at least the complexity, but I'm not sure. I don't know.
It may be open.
That's an open question.
More questions? Okay, many thanks to you and another question?
By unambiguity, is that different from deterministic, or is it like...
No, this is different. The automaton can be not deterministic, but one path can be not accepted at all with the... So there, it can be... So this state is accepting. There we can have an A and a C So this is not deterministic, but this is unambiguous.